Okay, in the second part of section 9.2, we continue to discuss the hypothesis or significance testing with population proportions. We will compare the population proportion, a two-sided hypothesis test, with sort of an equivalent confidence interval. And then we'll get to a very abstract and sometimes probably the most confusing topic that we discussed this year, something called the power of a test. And so we're going to go through an example, a four-step problem example that we will then use in our discussion of power. All right. The results of significance tests is basically a decision to reject H naught or fail to reject H naught. When we reject H naught, we are often left wondering what the actual proportion P might be. So a confidence interval, is what we used in the previous chapter to sort of come up with an estimate for what it would be. All right, so let's look at an example. Tyen found that 90 of a simple random sample of 150 students said that they never smoked cigarettes. The number of successes and the number of failures in the sample are 90 and 60 respectively. So we we can think about proceeding with our calculations. So, our large count condition holds. We randomly sampled. We're not sampling more than 10% of the students at a school. So all of our conditions are held. So also notice that we have set up a null and alternative hypothesis, that 50%, there are 50% people who have never smoked, and the alternative we're setting up is that it's just not equal. So it's a two-sided test in this case. All right, so the confidence interval in that case, if we use the p hat plus or minus z star, and then square root of p hat 1 minus p hat all over n, we get an interval. We put all that in, we get an interval of 0.522 to 0.678. All right, so we are 95%, the conclusion, we are 95% confident that the interval from 0.522 to 0.678 captures the true proportion of students at his high school who say they have never smoked a cigarette. All right, so what is sort of the link between that two-sided test that we would take and the confidence interval? So normally when we do significance tests, we're not doing a confidence interval, but there is a relationship between a two-sided test and the confidence interval. So the 95% confidence interval gives an approximate range of P naughts that would not be rejected by a two-sided test at the alpha level of 0.05. So a 95% confidence interval that we did last chapter gives us a set of plausible values. And before we started doing significance tests, remember we said if someone has a claim about a particular value, if it's outside the claim, then we would say, our evidence does not support that claim. And if it was inside our interval, then that would be evidence to support that claim. And so really that's kind of what hypothesis test is. You are setting a certain claim, P naught is equal to a certain value, right? The hypothesized value is set to a certain value, and then we either reject it or we don't reject it. So but this only works for a two-sided test because that's what an interval sort of confidence interval is. It's on either side of our p hat. So it's a two-sided situation. All right. So a two-sided test at significance level alpha, so usually we use a 0.05, and the 1 minus alpha, so that would be a 95% confidence interval. If we're using a 5% alpha, the corresponding thing would be a 95% confidence interval. They'll give similar information about the parameter. Now, they're not exactly the same because we use slightly different, for confidence interval, we don't have a claimed value. So we don't have a hypothesized value of P when we do confidence intervals. We use P hats in the calculations. When we do a significance test, what do we use in our calculations? Well, we use the hypothesized value. We assume the sampling distribution is centered on that hypothesized value. So they give similar information and similar range of values, but not exactly the same. All right. Type 2 error and the power of the test now. So power, we're getting into our discussion of power here. So significance test makes a type 2 error when it fails to reject a null hypothesis. And when you really should. So when it's false. When the null hypothesis is false, we hope that we would reject it, but a type 2 error will occur when we fail to reject it when it's actually false. Now, we didn't make a mistake. Again, it's the sample that indicates to us, and the sample statistic that indicates to us whether we should reject the null hypothesis or not. And so sometimes we get a sample that indicates that we should not reject it. So we failed to reject it. And so did we make a mistake, right? That's kind of what we're talking about in a type 2 error. Again, it's not an error that you made in calculation or whatever. It's just that sometimes we get an alpha level. Sometimes we get a sample statistic that indicates that we should not reject the null hypothesis, but sometimes it's actually the null hypothesis is actually false, but our sample was not extreme enough to indicate that we should do that. All right, there are many values of the parameter that make this alternative hypothesis, HA, true. In other words, that would cause us to reject the null hypothesis. So some new alternative hypothesis. All right, so the probability of making a type 2 error depends on several factors, including the actual value of the parameter. So we have a hypothesized value, but what's the true value? That will affect whether or not an error occurs. A high probability of a type 2 error for a specific alternative parameter value means that the test is not sensitive enough to actually detect that the actual parameter or actual proportion in this case is actually higher or possibly lower depending on what direction we're talking. All right, a power. So the power of a test against a specific alternative. So the power of a test will be always related to some alternative value. Okay, the power of the test, it's the power to detect that alternative value and as a result reject the null hypothesis. So the power of the test against a specific alternative is the probability that the test will reject the null hypothesis at a chosen significance level, alpha, when the specified alternative value is actually the true parameter. All right. Now, that definition is going to make no sense to you until you think about it a couple times and we go through an example. So let's read through it again. The power of the test against a specific alternative. So that power, how powerful the test is going to vary based on what the alternative parameter is. So we think a certain value, but the real world, it's something else. And so depending on what that something else is, the power of the test will vary based on that alternative value. Okay. And again, hopefully after our discussions, all this will make a little bit more sense. So again, let's just read through this again. The power of a test against a specific alternative is the probability that the test will reject the null hypothesis at a chosen significance level alpha when the specific alternate value of the parameter is actually true instead of the null hypothesis, instead of the hypothesized value of the parameter in our test. All right, so we're going to go through an example that we will use to further explain power and talk about power. I've created a Desmos file that will sort of help visualize what power is in the form of a shaded region under under a sampling distribution normal curve. All right, so first let's go through this example. This example of a four-step process. All right, a potato chip producer receives a truckload of potatoes, and he'll clean them and slice them and make potato chips from them. But he wants to reject the entire load of potato chips if there's enough evidence that more than 8% of the potatoes have blemishes. So he's going to use them. If it comes in, if the truck is 8% blemishes, he's okay with that, right? It's not too many blemishes. But if it's got more than 8% blemishes, then he's going to reject it because that's too many blemishes. He doesn't want his potato chips looking all crappy from all the blemishes in the potatoes. All right, so again, here you have the entire question on your paper, but here I've hidden part of the question so that we can come up with our null and alternative hypotheses without having looked at the sample. So what are we scared of here? Are we scared of truckloads having blemish rates less than 8%? Or are we scared of blemishes that are truckloads that have blemish rates above 8%? So clearly we don't care if they're less than 8. The potato chips will look even better if they're less than 8, but it's over 8 where we have a concern. So that's where we come up with our null and alternative hypotheses. We want to test H naught is that P is equal to 8. The alternative is that P is greater than 8%. And we're going to use an alpha of 0.05. And we want to say what P is in our state. So P is the true proportion of blemishes, of blemished potatoes in the truck. All right, so we want to do a plan. Our plan states our inference procedure. So we want to do a one sample Z test for proportions, and we're going to select a random sample. We're going to assume there's more than 5,000 potatoes in the truck of potatoes. And then we want to check our large count conditions. So a sample size of 500 times the hypothesized blemish rate of 8%, that's 40. And 1 minus that, that's 460. So both of those are over 10. So we know our sampling distribution of p hat is approximately normal. All right, so that's our plan. All right, now we want to calculate, do our do. So we first calculate our p hat, calculate our test statistic, our z, and then calculate our p value, again, which is the probability. All right, so our p hat in our sample, he finds that out of the 500, 47 of the potatoes have blemishes. And so that's a p hat of 0.94%. And that corresponds to a z-score of 1.15 and a p-value of about 12%. All right, so that is not that unlikely. We have a almost 12.5% probability that we would get a p hat as extreme or more extreme than 9.4%. When the true proportion still is 8%. So it's not rare enough for us to reject this load of potatoes. All right, so since our p-value of 0.1243 is greater than our alpha of 0.05, we would fail to reject it. And then we would say that there's not convincing evidence that more than 8% of the potatoes on the truck have blemishes. Now, our p hat is higher than 8%, but we would expect that sometime, right? We would expect our samples to vary above and below 8%. Even when the blemish rate is actually 8%, we're going to expect that our sample, our sample statistic p hat, will vary above and below, slightly above and below 8% when the true blemish rate is 8%. And so how often would we expect it to be as high as 9.4% or higher? We would expect that to happen just by chance 12% of the time. So we don't think that that's rare enough, so we're not going to reject these. This could have happened 12.5% or so of the time when the blemish rate truly is 8%. So this is not evidence or strong evidence to say that the blemish rate is above 8%. All right, so we're going to use this idea of this 8% blemish rate to look at this idea of power. All right, the potato chip, so type 2 air and power of a test. All right, so the potato chip producer wonders whether a significance test that we've set up, this p-value of 0.08 versus the alternative of p-value, the p proportion, true proportion being greater than 8%, based on a random sample of 500 potatoes, has enough power to detect a shipment. And we have to have, if we're going to talk about power, we have to say, okay, some alternative p-value. So we really hope that none of the truckloads have a blemish rate above 8%, right? That's what the manufacturer is hoping for. But now we want to know, well, let's say that the blemish rate comes in at 11%. All right. Of course, we won't know this, right? It's not like it's labeled on the side of the truck. So it comes in and like, okay, well, if it comes in at 11%, we actually hope that we would reject that truckload of potatoes. And so how strong is our test? What's the probability that we would reject this truckload of 11% blemish rate, which is what we should do when it comes in? Because again, just because the truckload comes in at 11% blemish rate, our sample that we take is going to vary. And so sometimes it might be, the sample might be low enough so that we would fail to reject the null hypothesis. And this would be a type 2 error. And so that's what this is talking about, right? So we kind of see here the threshold. So we have the shaded region at the bottom here. This shaded region down here is indicating the alpha, right? Our 5% shaded region here. So if we look down below, we can see that about 10%, 0.0999, or about 10%, if our if our p hat from our sample or the sample statistic comes in above 10%, then we'll be down in this shaded region over here and we will reject the null hypothesis. We will reject that the blemish rate is 8% when the sample statistic p hat is above 10. So this green line on this slide shows sort of the threshold. If our p hat is above that, let's just call it above 10%, we're going to reject the null hypothesis. When it's below that, we will fail to reject the null hypothesis. Okay. And so earlier, we decided to reject the null hypothesis at an alpha level of 0.05 if our sample yielded a sample proportion to the right of that green line. Okay, so if 11%, if the blemish rate comes in, and if the true sampling distribution is centered on this 11% value, then we're here, right? And so remember, to the right of 10% blemish rate in our sample, we would reject it. So the shaded region on this graph shows the probability that we would reject the null hypothesis. Now, notice this sampling distribution is centered at 11% because that's the true blemish rate of the truckload of potatoes. Now, again, this is all theoretical because this truckload comes in and we don't know if it's 11%. But if it comes in at 11%, the sampling distribution would look like this. Again, some of the samples, most of the samples will be about 11% from this truckload, but some might be slightly lower than 10%. If our p hat, our sample statistic, is below 10, we will fail to reject the null hypothesis. And so that's a type 2 error. Because we should be rejecting this truckload of potatoes, because if the true proportion is 11%, that's certainly higher than 8%, and we want to reject it. But sometimes our sample will be out here on the left, and we will fail to reject it. That's a type 2 error. If you see to the right of this green line, then we will see that this shaded region in this graph shows us the probability that we would reject the null hypothesis when we actually should, and that's what the power is. The power is the probability that we would reject the null hypothesis based on some alternative hypothesis. The alternative hypothesis here is 11%. All right, so I'm going to go to a Desmos file to help kind of visualize this even more, and it's more dynamic, and we'll be able to play around with this some on the Desmos file that I'm going to go into now. But before we go there, let me just say one more thing. Since we reject H naught at an alpha level of 0.05, if our sample yields a proportion, our sample, that's our p hat, above basically 10%, we'd be correctly rejecting that shipment at 11% blemish rate 75% of the time. So that's exactly what we're talking about when we talk about power. All right, so this kind of helps us visualize it a little bit more, what we were just talking about, without the two sampling distributions right on top of each other. You can see, our alpha up here. The power of the test is shaded here. Now, again, that power is based on what the alternative p-value is, in this case, 11%. As that changes, as the truckload comes in, the power of the test will change depending on, the proportion of blemished potatoes in each truck that comes in. Ultimately, we want to look at what kinds of things will affect power. We'll talk about that more when we get to the Desmos file here. And from here, we will go to the Desmos, and then we'll come back and talk more about the different things that affect power. We'll talk a little bit about Desmos, but we'll kind of wrap it up and answer some questions about that as we get to the later slides. All right, so I made up this Desmos file in an attempt to sort of simplify and visualize so that you could visualize what power is. Okay, so I set this up sort of looking at the example we just did with potato chips and the blemish rate for the potatoes coming into the factory that we're going to use to make potato chips. And so if we look at this, and so the sampling distribution is centered at the hypothesized proportion of blemishes, which is 8%. So if the potatoes come in with 8% blemish rate, we're okay, and we're willing to use those potatoes to make potato chips. If there's strong evidence that the potatoes, when they come in, are higher than a blemish rate of 8%, then we want to reject those potatoes and not use them. Okay, so we've centered our sampling distribution on 8%. And so we're going to take a sample, right, from this truckload of potatoes. So we have, say a p hat here. So let's say our p hat comes in at just above 9% blemish rate. Now, that doesn't mean that the blemish rate of this truckload of potatoes is actually over 9%. If we really thought it was over 8%, we're going to reject it. But we want to look at and say, well, okay, maybe that how likely is it that we would get a blemish rate of just over 9% in our sample when the true blemish rate is only 8%? And that is that shaded region to the right of our statistic, our p hat of just over 9% blemishes. So our sample is, say, around 9%. Let's just make it exactly 9%. So let's say our sample of potatoes comes up with a p hat of 9%. So what's the probability that this would happen, or a blemish rate higher than 9%, when in our sample, when the true blemish rate is really 8%? So we wouldn't expect, again, our p hat to be exactly 8%. It's going to fluctuate, right? But we want to think about, well, what's the probability we would get a p hat as extreme as we got, or one more extreme, when the blemish rate is 8%. And that is that shaded region, in this case to the right, because we're above it. Okay. Now, if the p hat was below 8%, let's say we got a p hat down over here, then of course that we would never reject. That would be evidence, because look at the shaded region now. It's over 50% that we could have gotten this just by chance alone. So we're only going to be concerned if our p hat is above 8%. We're going to say, okay, let's say our p hat comes in at 9%. What's the probability that could happen just by chance alone when the true blemish rate is still only 8%? And that's rather high. You can see that's the shaded region to the right side of 9. Okay. Now, the further down our p hat gets, of course, the shaded region gets smaller, and so that means the probability that this could happen when the true blemish rate is 8% gets a little bit smaller, right? And so once we get past, as it turns out, the shaded region there in the red, that represents our alpha level of 5%. So if our p hat, as it turns out, it just happens to fall right above 10% blemish rate. So if our sample comes in at 10 or a little bit higher than 10%, then the probability we would get that extreme or one more extreme than about 10% is pretty low. And so that's starting to show evidence that maybe the blemish rate is not still 8%, but instead it's actually higher, because it's not very likely to get a p hat in this range out here when the blemish rate is truly 8%. So we could get a sample, an extreme sample, sometimes, but most of the time we're not. So when we're down in this region, right, and the further away we are, the smaller that little shaded region is. You almost can't even see it because of the red there. But the shaded region gets smaller. And once that shaded region is smaller than the red region, which is our alpha level, then we're going to reject that the true proportion of blemishes is 8%, and instead we're going to think it's higher than 8%. All right, so that's the whole idea of like the sampling distribution and rejecting the null hypothesis versus not rejecting the null hypothesis. We all already know that from our past examples. But what we want to look at and think about now is power. So power, let's kind of zoom in and change. So power is based on some alternative value. So that's what we call PA. So let's say that PA, so the truckload of potatoes comes in, and the blemish rate, let's start with something simpler. Let's say the blemish rate is 11%. So truckload comes in, the the um, the proportion of blemished potatoes in this truckload is 11%. Now we don't know this, right? The truckload comes in, we take a sample. Now, the p hat could be anywhere, right? So we expect the p hat to be somewhere in this range, because if the true blemish rate, unbeknownst to us, the true blemish rate is 11% on this truckload that comes in, we go and we take a sample. Sometimes we're going to be in this range, right? Most of the time, right? Because that's kind of closer to what the true sampling distribution looks like. Sometimes we'll be in the extremes out here, or sometimes we'll be the extremes out here in the sampling distribution. Well, what happens if our sample comes in out here? Well, that means we are going to fail to reject the null hypothesis. Because remember, the whole thing is based on this red sampling distribution centered at 8%. That's our test, right? So we're going to reject it if the blemish rate in the sample is bigger than 10%, because then it's less likely, very unlikely, that the true blemish rate is 8%. But if 11% is the blemish rate coming in, how likely are we to reject it? Well, if the p hat is beyond 10, above 10, we will reject the null hypothesis. What percent of the samples that we take from this truckload with a blemish rate of 11% would get rejected? And so that is the shaded blue region, everything above 10. So I'm guesstimating that to be about 75%. So about 75% of the samples that we would take from a truckload with a blemish rate of 11% blemishes, about 75% of those samples would be rejected by our test. All right, and so that is the power of the test, but it's based on this alternative proportion of blemishes set at 11. So that blue shaded region, how much of the curve under the the green sampling distribution with the blue shading there, that's going to change, right? So the as the proportion of blemishes changes, like let's say the truckload comes in and the alternative is at 12%. I get to stop at 12. Now you can see again, if our p hat is anywhere above 10, we're going to reject it. So our test is stronger when the truckload of potatoes comes in at 12% blemish. Our test is going to reject that truckload more often. Occasionally, we're going to make a mistake and fail to reject it. If our sample happens to be out here about 5% of the time, it looks like, then we would fail to reject that load of potatoes and use the overly blemished potatoes. So the blue shaded region here is representing the probability that we would reject the null hypothesis and say that the blemish rate is actually higher than 8% when the blemish rate is actually 12%, right? So when the true blemish rate is 12%, we're going to reject it, I'm guesstimating about 95% of the time. But the power of the test is connected to the actual blemish rate that comes in. It's unknown to us. We don't know, right? But we want to be able to say, oh, what's the power of the test? It's the probability we would reject the null hypothesis and say, oh, the blemish rate is higher when it actually is higher, right? And it's set at a particular value. So if the blemish rate coming in as 11% blemish rate, what's the power of the test? And so that's what we're showing here, this blue shaded region. It's about 75% or so. And then as we go over further, we can see, oh, the power. So 13% blemish rate comes in. What's the power of our test to reject the null hypothesis? Almost 100%. You can see there's a little bit of unshaded region there, so nearly 100%. So the test is very powerful for a truckload of 13% blemishes, where of course it's less powerful if we try to detect a 10% blemish rate. Only about 50% of the time would we reject that truckload. And we should reject it because the blemish rate is 10%. It's higher than our threshold, that what we want of 8%. But so that the power of the test is connected to and different every time we have an different alternative proportion. So that alternative proportion, often we just don't know what it is. Like that truckload of potatoes comes in, we don't know what the true blemish rate is, but we'll say, oh, how powerful is the test to reject 11% blemishes, to reject 12% blemishes. So you can see here, and it kind of makes sense, I think, if you think about it, we are less likely to reject. If a truckload comes in at 9% blemish rate, we're not very likely to reject that at all because it's just too close to our 8% that we have as our maximum. You can see here now the blue, again, if we got a true truckload blemish rate of 9%, we would take samples from it, and the p-hat would vary, right? The p-hat would vary from sample to sample. Occasionally we'd be out here, in which case we would reject the null hypothesis. So again, that blue shaded region shows the probability that we would reject the null hypothesis and say the blemish rate is higher. Which is really what we want to do. But our test is not very powerful when the truckload comes in at 9%. It's only about 25% of the time would we reject that truckload, even though the truckload blemish rate is higher than our 8%. Okay. All right, so what kinds of other things are affecting? Let's move this back. Let's say we're at 12%. Let's do 11. We're at 11% blemish rate. What kinds of things affect the power, which is that shaded region? So if we increase the sample size, so remember, think about this, the sample size increases the spread or standard deviation of our sampling distributions will decrease. So both of these sampling distributions will get a little narrower and a little taller. So let's do that. Let's slightly think about that blue region and what percent underneath this sampling distribution centered at 11, what's happening to the percent underneath of the blue region. So as it gets smaller, notice more and more of that sampling distribution is blue. So that means the blue shaded region represents the power. So as the sampling distribution, as the sample size increases, the standard deviation of the sampling distribution gets narrower, gets smaller. And so look what happens. The blue shaded region gets bigger. So the power increases as we increase our sample size. Okay. All right, let's get it back to about where it was. I think it was about there. Okay, so that's one way to increase the sample size. I'm sorry, one way to increase the power is to increase the sample size. Another way is to, what we say is increase the effect. That means the difference between the hypothesized value and the alternative hypothesis is greater. So as my blemish rate increases, the power to detect that big blemish rate increases. So almost 100% of the time we would reject a truckload with a blemish rate of 13%, and that would be a higher power than if the truckload came in at 9%. The probability we would reject that truckload is much smaller, about 25%. So it is the effect or difference between the hypothesized value and the alternative value increases, so does the sample size. All right. And then also, what else? If we, notice that the blue shaded region ends with our alpha level. So if we increase our alpha level, in other words, if we increase our alpha level to 10%, so that's an alpha level of 0.05. If we increase it, we double that area, let's say about there is about doubling it, then that also increases our blue shaded region, that threshold about which we're going to reject. So that increases the power as well. So three things that are in it going to increase the power. Increasing the alpha level increases that blue shaded region. Increasing the sample size increases that blue shaded region, because we increase the sample size, we are decreasing the spread of the sampling distribution. And then the effect, like increasing the effect between how much difference there is between the hypothesized value and the alternative value, is that effect is bigger, the power gets bigger as well. So the power of the test is more powerful to predict a 13% blemish rate than a 9% blemish rate, because the effect, the difference between that alternative hypothesized value is bigger at 13 than it was at 9. All right, so let's continue our discussion of type 2 errors in power of a test. So this is really what it boils down to. And you're not expected on any kind of assessment to be able to figure out what the power is, because you're not going to have those shaded regions that we saw on my Desmos graph. So you're not going to be able to say, oh, when the alternative proportion or parameter is 12, what's the power of the test? What happens when it's 13? What's the power of the test? You're not going to have to be able to calculate what the power is, but what you need to know is what affects power. As you do change one thing, does the power go up or down? That kind of thing. So sample size. So how does sample size affect the power of the test? Given everything else staying the same, if I increase my sample size, so as n increases, the sample size increases, so does the power. All right, the significance level alpha. Again, as I increase alpha, the significance level of the test, the power also increases. We saw that. We saw both these things on the Desmos file as we moved things around. And then the last one is the difference, or sometimes known as the effect. So it's the difference between the hypothesized value and the actual value. So the power of the test when the truckload of potatoes was 11% blemishes, and then what if it was 13%? So the effect or difference was larger at 13, so the power should be bigger at 13 than it was at 11. So as the difference increases, so does the power. All right, significance level of the test is the probability of reaching the wrong conclusion when the null hypothesis is actually true. So that's that shaded region on the right. That was on our graph on this example. That was the shaded region to the right. So that's the type 1 error. The power of the test to detect a specific alternative is the probability of reaching the correct conclusion when the alternative is actually true, when the blemish rate is 11% or 13%. The power of the test is the probability we'll do the right thing and reject the null hypothesis because of that alternative value. Okay, so we can just as easily describe the test by giving the probability of making a type 2 error. So type 2 error, sometimes we'll call it beta, is related to power. It is 1 minus the power. So power is equal to 1 minus beta, or beta is equal to 1 minus power. beta and the power add up to 1 is another way of looking at that. All right, so let's try answering some questions to help us check to see, do we really understand what this power and this beta, the power probability of a type 2 error, what that is. So think back to the example on the potato chip producer. What type of error, type 1 or type 2, is more serious for the potato chip manufacturer? So remember, type 1 error would be rejecting the null hypothesis when it's true. So that would be saying your sample suggests that the blemish rate is actually higher than 8% when it really is just 8%. Or the type 2 is you failed to reject it when it actually is higher, when the blemish rate is higher. All right, so I think we all agree that type 2 would be failing to reject it when you should would be worse for the potato chip producer. If he rejects a truckload of potatoes that are still actually good, then okay, so he's wasted those potatoes, but he's not going to get bad potato chips. So the worst thing for him is if he fails to reject a truckload that has a high blemish rate, and he gets a sample that indicates that he shouldn't reject it when he actually should, that's a type 2 error. And so his potato chips are going to have more blemishes as a result. All right, number 2. Based on your answer, should we choose a significance level of alpha level of 0.01, 0.05, or 0.1? 10%. All right, so remember that increasing alpha increases the power of the test, and that's what we want to increase. We want to decrease beta, or the probability of a type 2 error, but we want to increase power, which means that we should increase our alpha. So for the potato chip producer, an alpha level of 10% would be better. All right, now that's not meaning that that would be better for the farmer, because if we increase our alpha level, then there's a chance that we could be rejecting, that's a higher probability of rejecting the null hypothesis when it's actually true. So that means farmers are going to have their truckloads of potatoes rejected more frequently when they really shouldn't be. Okay. Tell if each of the following would increase or decrease power of the test. Okay, so 1, changing the significance level from 0.05 to 0.10. All right, so that's an increase in alpha level, so that will increase our power. All right, taking a simple random sample of 250 potatoes rather than 500. So that is decreasing our sample size, so that is going to decrease the power of the test. So we would rather have higher sample sizes to increase our power. Insist on being able to detect 11 instead of 12%. So these are talking about alternatives. So if the alternative hypothesis went to 11% rather than 12%, that means that it's closer to 0.8, 8%. And so we are decreasing the difference or the effect, and so that will decrease the power. And that's basically what it boils down to, is you need to know these 3 things. What 3 things affect power? So it's the change in alpha level, change in sample size, and the change in the true alternative parameter. All right, so this is your homework. You have 1 4-step problem. That's number 47, and this homework is due next class.